You guys see the notes there? Anyone just thumbs up, nods? You guys see that? Okay, great. So we are talking about inverse trig functions ultimately. And like I said, if you're able to have two screens and have these notes open, that's great. If not, just on a piece of paper, maybe jot some of these things down. But before we start talking about the trig functions specifically, if I just asked you about the 3, 5, and 7, 4, they make up a set I'll call A. And then if I ask you for A inverse, the relationship when we're talking about inverse functions, if you'll recall, is the set of those opposite xy points. So for every xy that exists, that yx point would exist for the inverse. So what I mean is the set that would make up A inverse is the point 1, 2 instead of 2, 1. 5, 3, and 4, 7. And what the heck? There we go. That's the set A inverse. So you just switch the x and the y's. That's what we mean by inverse function. So for the example here, if y equals 2x minus 3, do you guys remember how to solve for the inverse? You probably learned this at some point. You have to switch x and y and then solve for y. So to solve for this y inverse equation, switch x and y, that's your first step. And now we want to isolate y. So that's going to be x plus 3 equals 2y. And then if I divide the whole thing by 2, I get x plus 3 over 2 equals y. This is my y inverse equation, which can be left that way, or if you wanted to write it in slope intercept, would look like that. That would be the inverse function. Now, graphically speaking, if we want to sketch this out before we head into our trig functions, and let's say, I'll flip this one over. The original function, will let be the red function, 2x minus 3. So if I go down 1, 2, 3, has a slope of 2. Let's see if I can make that look good. There we go. That looked like y equals 2x minus 3. Now the inverse, which I'll draw in green here, is 1/2 x plus 1.5. So now y is 1.5, the y-intercept, and then has a slope of 1/2. So up 1 over 2. It's going to get me, let's see if I can get a straight line there. Something like that. But I think I need to bring it down a little bit. Let's try that. Oops. So there's y and y inverse graphed. And perhaps you're thinking to yourself, okay, I kind of remember this. The relationship that exists between those two graphs, them being inverses, visually, what's the relationship? Well, because we switched x and y to get the inverse from the original function, they are mirror images of each other about the line y equals x. So we'll sneak that in here. This is the line y equals x. So hopefully, if my picture is not too crummy, you can see that if I were to spin that red graph around that y equals x dotted line, it would land on the green one. So this would spin to here, and that would spin to there, and it would fall on it. Fair enough? That's the relationship for inverses. So when we come down to our trig functions, y equals sine x, we know, looks like this. That's negative 2 pi and 2 pi. There's 2 periods of the sine graph. The inverse is going to be y equals sine inverse of x. That's going to be how we write the inverse for the trig function. This is read as sine inverse of x. And I'll show you another way you can write that in just a minute, but that's kind of the introductory way of talking about these inverse functions. And so to get this inverse graph, if we think back to what we just did and said, okay, I need to draw the line y equals x and spin that blue graph around, that's going to get me my graph. Let's try and do that. That green graph is the inverse graph. Did I do a pretty good job? Does that look like a mirror image about the line y equals x? If you turn your head,
That's pretty good.
45 degrees. Thank you. That just takes one. Appreciate it. That's going to be our sine inverse graph, that green guy. So I'll redraw it over here. There we go. And what's going to be of interest to us are a few things. First of all, the domain of the inverse, the restriction on x, we know that that's going to be 1 and negative 1. Because if we go back to our original function, we know that the restriction on the range was 1 and negative 1. So that restriction, which was in terms of y for the original function, is now the same restriction in terms of x for the inverse. The x's and y's just switch. Everything that's true about that function, you just switch for the inverse. So the other piece of this is that the domain of the original function is infinite, right? It goes on forever left and right in terms of the original function. Similarly, my inverse goes up and down. Currently, as it's written, it does that forever. Now, the whole piece of this, the big deal, is this green graph that I have, is it a function?
No.
Maria, I see you shaking your head. Great, good. I see some shakes and people saying no. Good. It's not a function. And let's see, if I'm looking at my list over here, Oliver, you happen to be on my screen right now. Why is that green one not a function?
There's more than one output for one input.
Perfect. Some of you are thinking to yourself, if I draw a straight line, right, it does not pass the vertical line test, right? So this green graph, as it's written, is not a function. Now, using this idea of the vertical pink line that I've drawn there, if I go back to the original blue function, y equals sine of x, what characteristic of the blue function would tell me that its inverse is not a function? Instead of drawing a vertical line down the green one, what could I have done to the blue one to say, oh, okay, it's not, my inverse is not going to be a function? Well, just switch x and y. A vertical line is the equation x equals some number. Over here, it's because the original function does not pass the horizontal line test. because it does not pass the horizontal line test, we know that its inverse is not going to pass the vertical line test. Does that seem to resonate? If the original function doesn't pass this, the inverse function is not going to pass that. Okay. So what we need to do is pull back and say, all right, I need to restrict my domain such that I create what's called a one-to-one function. So my blue y equals sine of x, that's a function, but it's not what we call a one-to-one function. A one-to-one function is one that has its inverse that is also a function. So what we need to do is restrict the domain of the original function such that it creates the same appropriate restriction on my inverse. So looking at y equals sine of x, if I cruise, let's just take the first quadrant, that pink arc right there. Have I violated a vertical line test or horizontal line test, more importantly, just looking at the pink part? No. If I were to continue going though, now I've got problems, right? All of a sudden, if it doesn't pass the horizontal line test, therefore it's not gonna be a one-to-one function. What if I go backwards from 0 though? Is that gonna work? If I go back into the fourth quadrant, that pink kind of S-looking shape does work. It passes the horizontal line test. If I were to keep going left from there, I'd have problems. So when it comes to the restriction for sine, we're only going to consider the part in Q4 and Q1 for our inverse function, which means if I come over here, that's going to be this piece. Okay, so the only part of this function that I really care about is in that pink box, because otherwise it's not a function. Now we said that the domain is from -1 to 1. Based on what we've done and what we've said, what does that imply the range is? What is this top value? This top of the box?
Pi over 2.
Good. Pi over 2. And similarly down here, -pi over 2. Because that's where we stopped, right? Rotating through Q1 and back through Q4. So that's our restrictions. And each trig function is going to have its own restriction when we talk about the inverse. What we can quickly do is look at cosine. And I'm not going to do all of them, but we'll look at cosine just real quick. And cosine looks like that. I could go back one this way. And again, we'll start at 0. And if I cruise into the first quadrant here, still 1 to 1, no problems there. If I continue, which I can now, into the second quadrant, no problems there. If I were to keep going, however, I start running into problems. It's not going to be 1 to 1 anymore. If I go back, I'm going to have problems. So I've restricted it as well as I can for cosine, which means, and let's look back here. My inverse, so if this is y equals cosine x, y equals cosine inverse of x is only going to exist in the first and second quadrants, as evidenced over here, right? That's Q1 into Q2. So this graph is going to look like that, where this is 1, that's -1, and this all of a sudden goes from 0 to pi. Okay, so That's as much as I'm going to do as far as showing you the restrictions, but they're different for each function. Another way to write the inverse is what's called arc sine or arc cosine, arc tan. It just means inverse sine. Because what we're doing when we switch x and y and solve for this inverse is, well, in the original function, let me go back up here. I would plug in x's to get y's. And when I'm plugging in those x's for y equals cosine x, what am I plugging in? Am I plugging in angles or am I plugging in trig ratios? Well, x is the angle, right? I would plug in an angle. I'd plug in 30 degrees. I'd plug in 60 degrees. I'd plug in 2 pi over 3. And I would get some number that represented the trig ratio. What the inverse does is for x now, I'm plugging in the ratio. And what I'm going to get back, y, is the angle. So this is a ratio. And y is the angle for the inverse, right? It's doing the opposite for me. So this notation might actually make a little more sense. The arc sine of x really means find me the arc or the angle whose sine or cosine, whatever it is x, x being that ratio. So the question that the inverse answers is, what's the angle? So based on what we know, and these are all things we ought to know, if I gave you y equals sine inverse of 1/2, that is asking the question, sine of what angle is 1/2? And while there are an infinite number of answers to that because of the circularity of the whole thing, what's the first quadrant answer? Sine of what equals 1/2? (30 degrees), right? Or pi over 6. Fair enough? That's what the question's asking. How about y equals tan inverse of -1? How about that one? And again, there's a couple of answers you might be thinking, and this is where the restrictions are going to come in, but this is going to be -45 degrees or -pi over 4. Okay? And the reason that it's that and not, say, for example, I guess what would it be? 3 pi over 4, right, or 135 degrees is because of the restriction that we're going to put on it. The tangent is going to be like sine, where it exists between -pi over 2 and pi over 2. And then how about arc cosine? So this is, again, a little different notation, but it's asking the same question. What's the arc or the angle for cosine to have a ratio of -rad2 over 2? And we talked about the restriction on cosine, right? It exists between 0 and pi. So I'm looking for a quadrant 2 answer here.
135.
Good. 135 degrees.
Yep.
Or 3 pi over 4. Cool. All right. So what I've got here are the restrictions, effectively. Written in kind of a funky way here, but when it comes to sine, the inverse at least, the x is going to exist between -1 and 1. The y is going to exist between -pi over 2 to pi over 2. And maybe what you want to write as a note to yourself, excuse me, is Q4 and Q1. Those are the two quadrants that it's going to exist in. Cosine's domain is also between -1 and 1. Its range is from 0 to pi. So I'm going to write Q1 and Q2. Excuse me. That's where cosine inverse exists. Lastly, tangent, its domain is actually all reals, because if I just take a quick sketch of tangent here, which looks like that, the inverse looks like that. There's the inverse tangent graph. So hopefully you can see that its x is all reals left and right. However, whoops, son of a gun. Let's erase that. There we go. This is pi over 2 and negative pi over 2. So again, this like sign is Q4 and Q1. Those are the quadrants that the inverse exists. So really the biggest part of inverse world are the restrictions, because I'm sure you're going to be pretty good at coming up with these answers, but there are going to be times where you're going to have to ask yourself, okay, do I need the quadrant 2 answer or do I need the quadrant 4 answer? If it's a positive answer, it's always going to be Q1. The negative answers are, though, going to depend. Is it Q4 or Q1? And really, to synthesize the information, the only time it's going to be Q2 is cosine and secant. All the other ones, if you have a negative answer, I'm looking for quadrant 4. All right, a couple of problems here just to wrap it up. Then I'll let you guys loose. You can ask questions, all that kind of stuff. But these are kind of goofy questions. The first two are pretty straightforward. And what this is asking you, and you want to start kind of from the inside out, is arc sine of 1/2. I think we already did this problem, right? It's asking what angle for sine gets you 1/2. And the answer to that, I think he told me it was 30 degrees or pi over 6. Now, what's sine of 30?
1/2.
It's 1/2, right? So they kind of undo each other. The sine and its inverse leaves you with the argument that you started with. Now, this isn't always true because of the restrictions. So we'll talk more about that when we get back. I think the ones I leave you with are more on the straightforward side. But how about arc cosine of cosine pi over 3? We start with the inside. Cosine of pi over 3. Is that also 1/2?
Yeah.
Yeah.
Okay. So that's 1/2. Arc cosine of 1/2 is asking you, okay, well, what angle gets me 1/2? And it's going to be pi over 3, or 60 degrees. So those first two, pretty straightforward. They undo each other. Now, the next two look kind of difficult, maybe, I don't know, but they're actually really great. I actually like these problems a lot. Because the inside here says tan inverse of 3/2. So what that question is asking is, what angle of tangent gets you the ratio 3/2? And does anyone know that? If anyone knows that answer, you can unmute yourself and let me know. But I don't know. Tan inverse of 3/2. So the neat thing about this problem is that I don't need to know. This answer that I get is some angle. I don't know what that angle is. But what do I know? I know that rotation got me a ratio of 3/2. So for tangent, in my reference triangle here, where's 3 and where's 2? Well, this is y over x, isn't it? So that's 3 and that's 2, correct? Which,
Yep.
if we do a little work, this is going to be the square root of, is that 13?
Yeah.
Now think about the question. The question is sine of that same theta. The theta I don't know, but sine of that same angle. What's the sine relationship in that triangle?
3 root 13 over 13.
Good. Okay, so what's actually neat about this problem, at least to me, and I understand that your definition of neat and mine are different, but is that you never needed to know the measure of the angle. You just wanted to know that same sine relationship that existed for that angle. So we'll take a look at this last one here. Arc cosine of negative 5/13. How about that one? Arc cosine of negative 5/13 puts me where?
Second quadrant.
Second quadrant. Good. Arc cosine of theta here. And cosine, I think we have that going on.
Yep.
And does that get us, is that a
12.
Pythagorean triple? There we
12,
go.
yeah.
Great. So I want the tangent of that relationship. That's going to be 12 over 5. Right? I just want the y over x of whatever this angle is that I don't know. I wanted the tangent. All right. Like I said, you guys have been great. You're hanging tough. That's it for these notes. So I'm gonna, let's see what I want to do. I want to stop.